a stick figure picture related to problems 2 and 3, where I have a center mass that's, let's say, right here. I crouch down so I can jump up, and my center of mass lowers to position y0, vertical position y0. And then I jump upward. Okay, so I spring upward, and at position y1, my center mass is here, and this is where I leave the floor. And then up here is where I stop rising. And this will be the maximum height. Now we're wanting to look at the energy relationships for this scenario. We draw a free body diagram. While in contact with the floor, the free body diagram looks like this. Okay? We have gravitational force acting downward and the floor pushing upward. Now, part of the reason the floor is pushing upward is because gravity is pulling me downward into the floor, compressing the floor, the material. The material then exerts a compensating force. And also, I'm pushing down even harder on the floor. So it provides a net force, or it results in a net force that's greater in magnitude than the force of gravity, giving me a net upward force, which is necessary if I'm going to accelerate upward. So here's our free body diagram. In the free body diagram, while between here and here, you can get rid of all this. It just looks like this. You have my mass, you have gravitational force acting down, and no other forces. We're ignoring air resistance and other forces. So the net force would be equal to the gravitational force. Okay, well, looking at the first phase of motion, we want to know how much work is done by each force. Well, there are only two forces. Okay, of course, we have then the net force. Net force is equal to the gravitational force plus the normal force. The work by the gravitational force is what? Well, it's equal to the dot product of the gravitational force and the displacement. There's an upward displacement. This could be taken to be my displacement vector here. It's obviously delta y1, which is y1 minus y0, multiplied by j, if j is, of course, regarded as the vector in the vertical upward direction, the unit vector. Okay, the gravitational force is going to be negative mgj. Okay, j, it's in the y direction. Mg, its magnitude is mg, mass times the acceleration of gravity, and its direction is downward, so it's got to be negative. Okay, well, we can do that dot product, and that's very straightforward. Doesn't look like I actually thought I'd done that somewhere here. It's been a little while since we did this. So, well, let me just go ahead and fill it in. That equals then negative mg times y1 minus y0, which I could also write as negative mg delta y1. And then the work by the normal force is just the normal force times j, normal force being in the upward direction, times the y1 minus y0j, dotted with the y minus y0j, and that equals Fn times y1 minus y0 equals Fn delta y. And this should coincide with our intuition, which simply tells us that when we're rising, when our displacement is upward and gravity is acting downward, we're going to get a negative, gravity is going to do negative work on us because its direction is opposite to the direction of the displacement. So we just multiply the magnitude of the accelerator, or of the force, the gravitational force, which would be the weight, times delta y1, and it's going to be negative. Okay, our intuition, normal force, is in the same direction as our displacement from y0 to y1. So the work done by the normal force is just normal force times our y1 minus y0 or our delta y. Okay, well, it's valuable to put this into vector notation because we're going to be dealing with cases where forces aren't parallel. We're going to have to do dot products or other types of analysis to get the work done by those forces. Okay, well, the work done by the net force then is just, well, here's the net force. It's this one, and that's here, plus this one, and that's here. And of course, that's equal to negative mg plus Fn times y1 minus y0. And I have it here, but, well, and of course, the y1 minus y0 could be delta y. Now, next question is, what's a change in kinetic energy? Okay, it's a change in kinetic energy related to the work done by any of these forces in any way. And the answer is, well, as we derived by simply substituting F over m into the fourth equation of motion, we learned that F delta S is equal to the change in 1/2 mv squared, so that the work in a situation where the uniform of uniform acceleration in one direction, we obtained the fact that the change in kinetic energy, which is the change in 1/2 mv squared, is equal to the product of the force multiplied by the displacement. So this is equal to the work done by the net force. So the work done by the net force is equal to the change in kinetic energy. So this is equal to this. So I've just got a quote here. Here's your dot product again to calculate the work by the net force. We don't have to do that again, but I've gone ahead and written out the result once more. Okay, so here's your change in kinetic energy because this is the work done by the net force. This accounts for the normal force and the gravitational force, normal force being greater than the gravitational force. Now, there's more, because what's the change in potential energy? Okay, well, the change in potential energy, and people didn't remember this, so you want to understand that we've defined in this course, we haven't defined potential energy, we've defined change in potential energy. Change in potential energy is equal and opposite to the work done by conservative forces on whatever the system or object is. So that in this case, the conservative force acting on the system is gravity, and it exerts a force negative mgj on the system being me. And we dot that with, well, I've done a dot product here, but I haven't got my J component in here. I really don't have much room to write it, so I'm going to just kind of sneak it in here. There's my J. Kind of overlaps the parentheses. Now it's overlapping my negative sign over here, so I'll have to put the negative sign a little higher. Anyhow, it may be hard to tell what that is, but there's the J that I left out. So we dot the force of gravity by the displacement vector, and we get negative mg delta y, the negative of negative mg delta y. In other words, the dot product is negative mg delta y, but since the change in potential energy is equal and opposite to this, we have a negative out here, and then we just get our mg delta y. Now I've got a couple of notation things to fix here. My notation changes. This should change what was the delta y here to delta y1. Delta y1 indicating the change in position from y0 to y1. And I couldn't stand that badly written expression there, so I fixed it, and it reads just as it was supposed to before. Okay, so we have this is our change in potential energy. So how does this relate to this expression? Well, here we have a negative mg delta y, right? Or delta y1, and an Fn delta y1. Well, I'm going to expand that. I've got the Fn times this, which is my delta y1, so here's my Fn delta y1, and here's negative mg multiplied by my delta y1, which is equal and opposite. It's the negative of the potential energy change. So my potential energy change is mg delta y1, my negative mg times the delta y1 I get here is going to be negative change of potential energy for the first phase. So where does that leave us? Well, remember that this expression here was equal to the change in kinetic energy. So the change in kinetic energy is still equal to this expression, and therefore to the negative change in potential energy plus the work done by the normal force. So that this equals change in kinetic energy, and the work done by the normal force, Fn delta y1, is equal then to the change in potential energy plus the change in kinetic energy. So the work done by the non-conservative force in this situation is equal to the sum of the change in potential energy and the change in kinetic energy. Well, this is just an instance of something that applies universally. The work done by non-conservative forces is equal to the change in potential energy plus the change in kinetic energy. And that's because the work done by the net force is equal to the change in kinetic energy. And part of the net force is the non-conservative force, and the other part is the conservative force. And the conservative force leads to the delta PE term in a way that you should work out and try to understand very clearly. Okay. And in a way that I've explained many times, I'm not going to digress into that explanation now. Okay. Now, from y1 to y2, what's the energy situation? And what are the answers to these questions? Well, the net force is equal to the gravitational force because that's the only force acting on the system. The change, the work done by the non-conservative force is zero because gravity exerts only conservative force, so there are no non-conservative forces acting. So work done by non-conservative forces is zero, and it follows then that since the change in potential and kinetic energies is equal to the work done by the net force, then the change in potential energy, and I'll call that delta PE2, and the change in kinetic energy, delta KE2, one referring to the motion from here to here, two referring to the quantities that are involved from here to here. The sum of the change in potential and change in kinetic energy is zero. Now, how does that make sense? Well, if I toss this thing upward, what happens? Potential energy increases. Potential energy only continues increasing so far because we only have so much kinetic energy to start with, and kinetic energy can't go down below zero. Why not? Because kinetic energy is 1/2 mv squared. M is a positive quantity, and v squared is a positive quantity. So the change in kinetic energy, 1/2 mv squared, can't be negative. So that we start with kinetic energy. We can't go down below zero kinetic energy. So our kinetic energy decreases, can only decrease so far, so our potential energy can only increase so far. These changes, of course, being equal and opposite since their sum is equal to zero. So change in potential energy is equal and opposite to change in kinetic energy. Here's our change in potential energy. Here's our change in kinetic energy. Gives us an equation we can solve for delta y2. Having been given y1, having found delta y2, we can determine y2.